Alright, so next we're going to consider the following example. And so for this example, we're going to find the Maclaurin series. Find the Maclaurin series for f of x equals 1 plus x raised to the k power where k is any real number. Alright, so for this example, what we're going to do, we'll start out with f of x, 1 plus x raised to the k power. So we take a look at f prime. So f prime, you're going to be looking at k times 1 plus x raised to 1 less power. Here f double prime, you have k times, and then k minus 1 times 1 plus x to 1 less power. And here f triple prime, you'll have k times k minus 1, same constants as before, then times k minus 2 times 1 plus x raised to the k minus 3. And so if you think about what your nth derivative would look like in general, well, notice here that, let's say you take a look at the f double prime of x. You get a k times k minus 1 times 1 plus x raised to the k minus 2. So the numbers being subtracted from k here and the exponent matches up with the order of the derivative here. So second derivative, k minus 2. Same kind of thing happens here. Third derivative, k minus 3. Now the factors that you're multiplying by out here, you got a k minus 1 for the second derivative. You got a k times k minus 1 times k minus 2 for the third derivative. And so what's going to happen is, when you take a look at this last factor before the 1 plus x shows up, the number you're subtracting from k is going to be 1 less than the derivative you're taking here. So here the same thing, k minus 2, 2 is 1 less than 3. K minus 1, 1 is 1 less than 2. So in general, if you're looking at the nth derivative, you would expect to have k times k minus 1 times k minus 2 all the way times k minus, well remember, the number that's going to be subtracted from k in that last factor before the 1 plus x, that number is going to be 1 less than the derivative you're taking. Well, if we're taking the nth derivative, this number needs to be 1 less than that, so you'll be subtracting m minus 1 from k. And then you'll have your 1 plus k raised to the k minus n. Because once again, the number being subtracted from k in the exponent is the same as the order of the derivative you're taking. Nth derivative, k minus n. But you could write this nth derivative of f at x as k times k minus 1 all the way. And if you distribute the negative here, you'd actually have k minus n plus 1. And then you'd have your 1 plus x, once again raised to the k minus n. Now we're going to need to evaluate each of these at 0. And what you notice is that f of 0, if you plug in 0 for x, we'll have 1 plus 0 or 1 raised to the k power. That's just going to be 1. F prime of 0, you'll have k times 1 plus 0 to the k minus 1. That's just going to be k. F double prime of 0, well, you'll have k times k minus 1 times 1 plus 0 to the k minus 2. Well, that's just going to be k times k minus 1. Your f triple prime of 0, k times k minus 1 times k minus 2 times 1 plus 0 to the k minus 3. Well, 1 plus 0 to the k minus 3 is just 1 to the k minus 3, or 1. So your f triple prime of 0, you get k times k minus 1 times k minus 2. And in general, when you take a look at this nth derivative of f at 0, we get k times k minus 1 all the way through k minus n plus 1 times 1 plus 0 to the k minus n. 1 plus 0 is 1. 1 to the k minus n is 1. So this nth derivative, you'll have k minus 1 all the way through k minus n plus 1. So once again, that's your nth derivative at 0. So if we're looking for a Maclaurin series, we can get it. Then we know that f of x is going to have the form summation n equals 0 to infinity of f of, or nth derivative of f at 0 over n factorial times x to the n. But let's keep in mind what the nth derivative of f at 0 is. It's this product. So you're going to get the summation n equals 0 to infinity, k to k minus 1 all the way k minus n plus 1 all over n factorial times x to the n. So that is our representation. Now the question is, where does this converge? And so we'll take a look. We'll take a look using the ratio test to try to figure out where it converges. So let's take a look at our a sub n and our a sub n plus 1. So a sub n will have k times k minus 1 all the way to k minus n plus 1 over n factorial times x to the n. But your a sub n plus 1, we're going to have k times k minus 1 all the way. And we're actually going to have one more factor up top. You'll still have all the way through k minus n plus 1. But the additional factor is going to be what you get when you plug in n plus 1 for n here. And so let's go over, we'll have k minus n plus 1 plus 1. Distribute the negative, you have k minus n minus 1 plus 1. And that means the negative 1 and the positive 1 are going to cancel out. You get k minus n. And then on the bottom, we'll have n plus 1 factorial. And all this is times your x sub n plus 1. So using the ratio test, we need to take a look at the limit as n approaches infinity. Absolute value a sub n plus 1 over a sub n. So when we do that, we'll get the limit as n approaches infinity. We'll have our k times k minus 1 all the way through k minus n plus 1 times k minus n times x to the n plus 1 all over n plus 1 factorial. That's going to be over a sub n, so we'll have a k times k minus 1 all the way through k minus n plus 1 over n factorial times x to the n. And of course we're taking the absolute value of this thing. But remember, dividing by this is equivalent to multiplying by its reciprocal. Lots of stuff is going to go away, however, because notice all these factors k through k minus n plus 1 show up on top, also show up on the bottom. So all this stuff is going to go away. You'll still have a k minus n that's up top. Your x to the n plus 1 over x to the n will give you x up top. And the n factorial over n plus 1 factorial will give you an n plus 1 on the bottom. And so this is equal to limit n approaches infinity. Absolute value k minus n over n plus 1. That's absolute value of x. But we could divide each term on top and bottom by n if we wanted to. You'd have a k over n minus 1 when you do that to the top, over 1 plus 1 over n at the bottom. As n approaches infinity, k over n and 1 over n are tending towards 0. So you get absolute value of negative 1 is 1 times absolute value of x. That gives you absolute value of x. So our limit is the absolute value of x. So we know that if the limit is less than 1, we have convergence. If the limit is greater than 1, we have divergence. So we know that the binomial series, which is what this is called, converges. The absolute value of x is less than 1 and diverges. The absolute value of x is greater than 1. So, what we got from this is the following note. This note is that if k is any real number, and the absolute value of x is less than 1, then 1 plus x raised to the kth power is equal to, well, take a look at what we have over here for your Maclaurin series, f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and so forth. So here our f of 0 is 1. Our f prime of 0 is k, so we'll get k times x. F double prime of 0, k times k minus 1. be over 2 factorial times x squared. And then we'll have a plus k. It's k minus 1. It's k minus 2. Over 3 factorial times x cubed. This just keeps going on forever. All right, so let's take a look at the following example. So we'll find the Maclaurin series for f of x. It was 1 over the square root of 4 minus x. And so we think about how we can write this a bit differently. So if you take a look at 1 over square root of 4 minus x, that's the same as 1 over the square root of 4 times 1 minus x over 4. Now, if you think about that for a moment, though, then what you have is following. 1 over 2 times the square root of 1 minus x over 4. But this could be written as 1/2 times 1 minus x over 4 raised to the negative 1/2 power. So, with that in mind, we could use binomial series with k equals negative 1/2. And so let's take a look at what this 1 over the square root of 4 minus x would turn into. Okay, so we've got, once again, 1 over square root of 4 minus x. Same thing as 1/2 times 1 minus x over 4 raised to the negative 1/2. But if you think about what that means, you're going to get a 1/2 times now, if you compare the 1 minus x over 4 to the negative 1/2 to the 1 plus x raised to the k, the negative x over 4 is going to play the same role that x does, and once again, as mentioned here, negative 1/2 plays the role of k. And so, what we're going to start out with is a 1 in this set of brackets. And then we'll have plus k times x. Okay, well, remember, we're replacing the x with a negative x over 4. We're replacing the k with a negative 1/2. So you have a 1 plus, and then a negative 1/2 times a negative x over 4. And then we'll have plus. You got your k, which is -1/2, times k minus 1, which is a -3/2. It's going to be over 2 factorial. And then times -x over 4 raised to the second power. And this is just going to keep going and going and going. But I think I do want to put maybe one more piece of the puzzle in there. Because if we take a look at this piece, once again, k is -1/2. So we'll have a -1/2, k minus 1 will be -3/2, k minus 2 will be -5/2. This will be over 3 factorial. Then we'll have times -x over 4 cubed. And so if we work on simplifying this a bit, maybe it'll look somewhat better. We can certainly hope. But we'll have a 1/2 still. We'll have the 1. And then the -1/2 times -x over 4 will give us x over 8, or 1/8 x. Then we'll have a -1/2 times a -3/2. Well, that's going to give us a 3/4, and then that's over 2 factorial. So let's go ahead and write that as, let's go ahead and write it as a 1 times 3 over 2 squared times 2 factorial. And then we'll have times x squared over 16. And then over here, got a negative times a negative times a negative, but then you also have -x over 4 raised to an odd power, so overall we're going to have a positive. We'll have a 1 times 3 times 5, and then 2 times 2 times 2 will go downstairs with a 3 factorial, so 2 cubed times 3 factorial, and times x cubed over 64. And so you could try to figure out what the general term might look like. So if I were to have, let's say, the nth power, maybe you have a -x to the 4th raised to the nth power, what might that look like? So what I would expect is I would have an n factorial on the bottom. I would have n different factors like this going from -1/2, -3/2, all the way through. And then I would expect to have a negative. Well, let's think about what that last factor would be. If I take a look at 2 times 3 minus 1, that gives me 5. Take a look at 2 times 2 minus 1, that gives me 3. So I'm thinking this last one's going to be 2n minus 1. over 2. Then we'll have our negative x over 4 raised to the nth power. But once again, you're going to have n different factors here multiplied together. So you'll have n negative signs here. You'll have this contributing n negative signs, which will give you 2n negative signs, or an even number, which means the overall thing is going to be positive. So this thing, you would end up with 2 times 2 all the way, n different factors. You'd have a 2 to the n. Then you'd have your 2 factorial, the n factorial joining in on the bottom. Then you'd have 1 times 3 all the way times 2n minus 1. Then you have x to the n over 4 to the n. Well, you take 2 to the n times 4 to the n, and that's going to give you 8 to the n power. So it looks like we can write this as 1 times 3 all the way times 2n minus 1 over 8 to the n factorial times x to the n. Now, does what we see here and here and here and so forth match up with that observation? Well, let's say you have n equals 1. 2 times 1 gives you 2, minus 1 gives you 1. So you're only going to have a 1 up top. That's what you have here. Times x to the first, right there. 8 to the first times 1 factorial. Hey, the same thing as 8. What if n is 2? 2 times 2 gives you 4, minus 1 gives you 3, so you'd only have a 1 times 3 up top. 8 squared, well, that's going to give you 64. And then times 2 factorial. 16 times 2 squared, 16 times 4 gives you 64. There's your 2 factorial as well. And so if n equals 3, you're going to have 1 times 3, and then 2 times 3, 6 minus 1 gives you 5, so you'll have a 1 times 3 times 5. That's what you're seeing here. Then you'll have x to the third, that's there. Then you'll have 8 to the third. Well, 8 to the third is going to give you 512. 2 to the third, 8 times 64, that's 512. Then times 3 factorial, well, that's showing up as well. So it looks like this is a valid general term for us. So this would be our representation. It's ugly, but it is a representation that we have in Maclaurin series for 1 over the square root of 4 minus x. Now if you're thinking about the radius of convergence, now remember, here we're saying, in fact here we said that as long as the absolute value of x is less than 1, the binomial series converges. But we also said over here that negative x over 4 was playing the role of x. And so what we would need is for the absolute value of negative x over 4, we would need that to be less than 1, which means that the absolute value of x would be less than 4. And as long as that's true, then you're guaranteed convergence for this particular series. All right. So, I've got a few more examples I want to show you, and then we'll be finished with this section. So here we're going to evaluate the integral e to the negative x squared dx as an infinite series. Well, if you think about one way to represent this, e to the x, 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, and so forth. This is a Maclaurin series representation for e to the x. So if I want to represent e to the negative x squared, then I can simply replace all the x's in this representation with negative x squared. And so we'll have a 1 plus negative x squared plus negative x squared squared over 2 factorial. So negative x squared cubed over 3 factorial, and so forth. And then this is going to mean that our e to the negative x squared is 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, and so forth. And so, what we get is the integral e to the negative x squared dx is going to be the same thing as the integral of 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, and so forth. And so our goal is really just to go term by term with this. We'll have our arbitrary constant, and then we'll add. When we integrate the 1, we get x. Integrate the negative x squared, we get a negative x cubed over 3. Integrate x to the 4th over 2 factorial, you'll get x to the 5th over 5 times 2 factorial. If you integrate the negative x to the 6th over 3 factorial, you get a negative x to the 7th over 7 times 3 factorial. And this will just keep it on. So in general, you could write this as c plus summation n equals 0 to infinity of negative 1 to the n, because we do have that sign change happening every time we go to our next term. And then all the powers of x that we have are odd, so we'll have x to the 2n plus 1. If n equals 0, that starts with x to the 1st. And this will be over n plus 1, because notice 3 have here matches with that exponent, 5 here matches with that exponent, 7 here matches with that exponent. But you also have, in this case, 1 times 0 factorial technically on the bottom, 3 times 1 factorial, 5 times 2 factorial, 7 times 3 factorial. And so if you write out your general term, this is what it's going to look like, and this will be our representation. Now, it turns out you can show that the series converges for all x, mainly by observing that the original series for e to the negative x squared converges for all x, all real x. All right. So let's take a look at the following. Let's evaluate the limit as x approaches 0, e to the x minus 1 minus x over x squared. Now, we have a number of ways that we can approach this particular limit. But here's what I think is kind of a neat way to look at it. So if you take a look at the limit as x approaches 0, e to the x minus 1 minus x over x squared, that's the same as the limit as x approaches 0 of, and let's go ahead and put our Maclaurin series representation in for e to the x. So you'd have your 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so forth. And minus 1 minus x. This over x squared. But the 1 here and the negative 1 here will cancel. The x here and the negative x here will also cancel. And so we end up with the limit as x approaches 0. X squared over 2 factorial plus x cubed over 3 factorial and so forth, all over x squared. But if I take x squared over 2 factorial and I divide that by x squared, it's essentially the same as multiplying by 1 over x squared. If I take x squared over 2 factorial times 1 over x squared, the x squared is going to reduce out, and I'm left with a 1 over 2 factorial. Now if I do the same kind of thing with x cubed over 3 factorial, x cubed and the x squared is going to reduce to give you x over 3 factorial. The next part will be x squared over 4 factorial and so forth. But if we're taking the limit as x approaches 0 of this thing, notice that every term after the 1 over 2 factorial is going to have x to at least the first power. And so if we plug in 0 for x, then all that's going to be left over is this 1 over 2 factorial, which is the same thing as 1/2. So it's just a different way that we can evaluate this limit. And now I have one last example I'd like to show you. And in this example, we're going to be finding the first 3 non-zero terms. In the Maclaurin series. And we're going to be taking a look at e to the x times sine x. All right. Well, if you take a look at e to the x times sine x, well, first off, this e to the x we already have representation for. In fact, I used it over here in the previous example. So we're going to have a 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so forth. And then our sine of x will have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so forth. And once again, I'm wanting the first 3 non-zero terms in this Maclaurin series. Well, think about what would happen if I were to start multiplying each term in this set of parentheses by each term in that set. Well, if I start out with the 1 times these terms, I'm going to get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so forth. Then I'll multiply x by each of these terms, and I'll have x times x is going to give us x squared. X times a negative x cubed over 3 factorial will give us a negative x to the 4th over 3 factorial. And x x times x to the 5th over 5 factorial will give us x to the 6th over 5 factorial. And then if I take x squared over 2 factorial times each of these, well, x squared over 2 factorial times x gives us an x cubed over 2 factorial. X squared over 2 factorial times x cubed over 3 factorial, or times a negative x cubed over 3 factorial, give us a negative x to the 5th over 2 factorial times 3 factorial. X squared over 2 factorial times x to the 5th over 5 factorial gives us x to the 7th over 2 factorial times 5 factorial, and so forth. And so notice the way that I've arranged these is I've 4 columns. X column, x squared, x cubed, x to the 4th, x to the 5th, x to the 6th, x to the 7th, and so forth. And I know that if I start multiplying x cubed over 3 factorial by each of these terms, the lowest power of x that I'm going to have is x to the 4th. If I'm looking for the first 3 non-zero terms, however, I'm not going to end up going beyond the x cubed term. And so I can essentially stop here because every other product that I'm going to generate is going to have x at least to the 4th power. And so what this means is that when I go to add all this stuff together, we'll have x plus x squared, then your negative x cubed over 3 factorial plus x cubed over 2 factorial. That's the same thing as negative x cubed over 6 plus x cubed over 2. Now, if you convert everything to a denominator of 6, x squared over 2 gives you a 3x cubed over 6. So this will give you a 2x cubed over 6 when you add these together, or x cubed over 3. And with that, section 11.10 is complete. So we'll take a look at some recommended exercises. 11, 13, 19, 21, 23, 25, 35, 39, 61, 63, and 67.